Okay, I have a confession to make. It's about a drawer in my kitchen. You know the one?
I think I do.
The drawer of shame.
Hmm.
It is just this tangled, dusty nest of cables that I haven't touched in like 5 years.
Yeah.
But I am absolutely terrified to throw any of them away.
Yeah.
Because, well, what if I suddenly need that one specific cord with the weird square end?
For a printer you owned in 2012.
Exactly.
Ah, the cable spaghetti. That's a universal human experience. It's the graveyard of dead tech.
It really is. And it's not just the mess, it's the mystery of it all. Like, why does this plug fit into my phone but not charge it fast?
Right.
Or why does my monitor look like a washed out watercolor painting if I look at it from like half an inch to the side?
Mm-hmm.
And why, for the love of all that is holy, are there 17 different things all called USB?
It feels chaotic, doesn't it? But there is actually a logic to the madness.
I find that hard to believe.
No, really. If you look closely at that drawer, you're not just seeing a pile of plastic and copper. You're looking at the nervous system of the personal computer.
The nervous system. I love that image.
That's exactly what it is. And that is our mission for this deep dive. We are going to decode the physical connections that make our digital lives possible. We're talking cables, connectors, displays, and the motherboard itself.
And we're pulling this from the CompTIA plus Core 1 and Core 2 training material, right?
That's right. To really decode what's going on under the hood, or I guess behind the monitor.
And just to set the stage for you listening right now, this isn't just trivia. I mean, if you've ever tried to build a gaming rig or just troubleshoot while your fancy 4K screen looks blurry, understanding these physical connections is literally step one.
It is. It is the foundation. If the physical layer isn't right, nothing else matters. You can have the fastest software in the world, but if you're pushing it through a bottleneck cable, you're going nowhere.
So here's our roadmap. We're going to start by hacking our way through the USB jungle.
A worthy quest.
Then we're going to look at the screens we stare at all day. Why some are gorgeous and some are just garbage. We'll talk about the war between HDMI and DisplayPort, and finally we're going to crack open the computer case.
Look at the internal organs. Sounds like a plan.
Okay, let's start with the most ubiquitous connector on the planet. USB, Universal Serial Bus. Now, universal is a pretty bold claim for a standard that seems to have 1,000 different shapes.
It is a bit ironic now, isn't it?
Mm-hmm.
But to understand why we have so many shapes, you have to go back to the beginning. Before USB, the back of a computer was a nightmare.
Oh, I remember.
Massive parallel ports, serial ports, those round PS2 ports for mice. USB 1.0 arrived in 1996 to unify all of that. But physically, it established a very strict relationship, the host and the peripheral.
The boss and the worker.
Exactly.
Right.
And this is the key to understanding the shapes. The Type A connector, that's the flat rectangular one everyone knows that goes into the computer. The host.
Okay.
The Type B was that square, chunky connector with the beveled corners.
The one that's still on the back of every printer.
That's the one. Now, why make them different?
I have no idea.
Safety. That square shape was for the peripheral device so that you physically could not plug a computer into another computer.
Oh.
Yeah, if you connected two hosts together directly with a male-to-male Type A cable, you'd create a power feedback loop that could literally fry the motherboards.
So the different shapes were a physical safety mechanism? That actually makes sense.
It was a key for the lock.
But then things started shrinking.
Right. Mobile devices happened. That chunky square Type B was way too big for a digital camera or a flip phone.
Yeah.
So the industry improvised. We got mini B, and then phones got even thinner, so we got micro B.
Oh, micro B. The flat little trapezoid with the little hooks that would always get pinned?
The very same. A fragile design, honestly. And that fragmentation, mini, micro, Type A, Type B, that is what led to the clutter in your kitchen drawer.
But then the revolution happened. Type C.
The Type C connector, it changed the fundamental rule. It's reversible.
A blessing.
A blessing in the dark, yes. No more up or down. But, more importantly, physically, it's capable of being both the host and the peripheral. It negotiates its role. It's the do-it-all connector.
It really is magical compared to the old days. But while the shape finally got standardized with Type C, the names for the speed seemingly went off the rails.
Oh, you're talking about the USB 3.x naming conventions.
I was reading the specs, and I honestly thought it was a typo.
No, it's, yeah. It is widely considered a branding disaster.
Okay, so let's unpack this. We started with USB 1.0, then 2.0 jumped to a 480 MIDI piece. Simple. Then USB 3.0 came out, super speed, 5 gigabits per second. I'm still with you.
And then the rebranding started. When the USB group released the 10 gigabit standard, they wanted everything to sound new. So they went back and renamed the old 5 gigabit standard.
Like they call it.
USB 3.0 became USB 3.1 Gen 1, and the new 10 gigabit speed became USB 3.1 Gen 2.
But it gets worse. Then came USB 3.2.
Correct. They did it again. So now, that original 5 gigabit speed, what used to be 3.0, is sometimes called USB 3.2 Gen 1. The 10 gigabit is USB 3.2 Gen 2.
And the new one.
And the 20 gigabit speed is USB 3.2 Gen 2 by 2.
Gen 2 by 2. Sounds like a math problem.
Yeah.
Or a piece of lumber.
It actually describes the architecture. It means it uses 2 lanes of data running at 10 gigabits each simultaneously.
So that's how you get 20.
That's how you get 20. But yes, for the average person, it is incredibly confusing. You can buy a USB 3.2 cable and not know if you're getting 5, 10, or 20 gigabits.
So the takeaway here is ignore the gen and just look for the GBP's number. Hopefully USB 4 fixes this.
Ideally.
Yeah.
Yeah, USB 4 unifies things quite a bit, largely by adopting the Thunderbolt 3 protocol, which we'll get to. It mandates the Type-C connector and can hit speeds up to 40 gigabits per second.
Blindingly fast.
Yeah.
But before we leave USB, we have to talk power. I remember plugging my old phone into my laptop back in 2010, and it would take like 6 hours to charge.
Because the original USB specs were pitiful on power. We're talking 0.5 watts.
That's nothing.
Just enough for a mouse sensor or a keyboard LED. It was never meant to charge a battery.
And
Now we have power delivery, or PD. With the latest PD 3.1 standards over USB-C, we can push up to 240 watts.
240 watts. That's not just a phone.
Right.
That's a gaming laptop.
It is. It's 48 volts at 5 amps.
Yeah.
It basically means we are approaching a world where you don't need a proprietary brick charger for your high-end hardware.
You just need one good USB-C cable.
One high-quality USB-C cable. And this is a huge, but you need a cable actually rated for that power.
Right. What happens if I use a cheap gas station cable to try and push 240 watts?
Best case, it just charges slowly. Worst case,
It melts.
the cable melts. The wire gauge inside those cheap cables is just too thin to handle that kind of amperage. So that kitchen drawer of shame is actually dangerous now.
Good to know. Okay, let's shift our eyes from the cable to what it's plugging into, the monitor.
Display technology. This is an area where people often just look at the size, I want a 27-inch screen, without realizing that the technology inside the panel dictates everything.
I learned this the hard way. I bought a cheap gaming monitor and tried to do photo editing on it. The colors just looked wrong. Like beige looked white and dark blue looked black.
You likely bought a TN panel. Twisted pneumatic.
Twisted pneumatic. Sounds like a heavy metal band.
It's the oldest LCD technology. The name comes from how the liquid crystals behave. They literally twist to block light. The advantage of TN panels is speed. They are incredibly responsive.
Which is why gamers like them.
Exactly. High refresh rates, low latency, low cost.
But the cost is the picture quality.
Correct. The viewing angles are terrible. If you slouch in your chair or look from the side, the colors invert or wash out. That's why your photo editing failed. You can't color correct if the color changes every time you move your head.
So for my photo editing, what should I have bought?
An IPS panel. In plane switching. In an IPS screen, the crystals rotate parallel to the screen plane, which gives you beautiful, accurate colors and wide viewing angles.
So I can look at it from almost anywhere and the image stays consistent.
Exactly.
Is there a downside? Or is IPS just perfect?
Well, historically, they were slower than TN, though they've really caught up. But their main weakness is contrast. Because there is a backlight constantly shining, it's hard to block it all out. So black usually looks like a dark, glowing gray.
Okay, so we have the fast, ugly TN and the pretty glowing IPS. Is there a middle ground?
That would be VA, or vertical alignment. It has much better contrast than IPS. The blacks are deeper and better colors than TN. But it suffers from color shifting at angles, and it can have some ghosting with fast motion.
It still feels like we're just shuffling compromises.
Yeah.
But then there's the new king on the block, OLED.
Organic light-emitting diode. This is a fundamental shift. In LCDs, TN, IPS, VA, you have a flashlight, the backlight shining through a shutter, the pixels. In OLED, there is no backlight.
Each pixel makes its own light.
Right. Each individual pixel creates its own light.
Which means if the pixel is off.
It is perfectly, treely black. Infinite contrast. The colors are stunning, and the response time is instantaneous. It's gorgeous.
You hear horror stories about burn-in.
That is the Achilles heel. Because the organic material degrades over time, if you leave a static image on the screen for hundreds of hours, it can leave a permanent ghost.
Like a health bar in a video
A
game.
health bar, a news ticker. The organic compounds in those pixels just wear out faster than the others.
So high risk, high reward. And so one more term, mini LED. What's that?
Mini LED is an evolution of LCD. It uses thousands of tiny LEDs for the backlight instead of just a few big ones. It gets incredibly bright, brighter than OLED, and it doesn't burn in.
But it's still an LCD at its core.
Exactly. Because it still uses a backlight, you don't get those absolutely perfect pixel-level blacks of OLED. You might see a little bloom around bright objects on a dark background.
Okay, so we know what screen we want. Now, how do we get the video signal to it? This seems to be a battle between two giants, HDMI and DisplayPort.
The video cable wars, and honestly, they've carved out different territories.
HDMI feels like the living room king.
It is. HDMI, high-definition multimedia interface, was built by TV makers. It carries video and audio easily, it handles HDR very well, and it's on basically every TV and console.
But if I walk into a professional office or a high-end gaming setup, I see DisplayPort. Why is that?
DisplayPort was designed for the computer industry, not the TV industry. It functions more like a data network.
What does that mean in practice?
It has some superpowers that HDMI generally lacks. The big one is MST multi-stream transport.
And what does that actually let me do?
It lets you daisy chain monitors.
Oh, that's cool.
Yeah, you plug your PC into monitor A and then run a short cable from monitor A to monitor B. You don't need two separate long cables going back to the computer.
That is a much cleaner setup.
It is. And DisplayPort has historically led the charge on adaptive sync like G-Sync and FreeSync. So on a PC, DisplayPort is usually the superior choice.
But wait, just to confuse things again.
Okay.
Sometimes I see a USB-C port acting like a video port.
Yeah.
And then there's Thunderbolt.
The Thunderbolt phenomenon. This connects right back to our USB discussion. Thunderbolt is an interface developed by Intel and Apple. Think of it as a tunnel.
A tunnel for what?
For everything. Thunderbolt tunnels other protocols through a single cable. It tunnels PCIe data, which is the language of the motherboard, plus DisplayPort video, plus power.
And it's had an identity crisis with its shape, hasn't it?
A big one. Thunderbolt 1 and 2 use the mini DisplayPort connector shape. They look like video cables. But then Thunderbolt 3 switched to the USB-C shape.
So a Thunderbolt 3 port looks exactly like a USB-C port.
Exactly, but it acts differently. Because it carries that PCIe data, you can do things you can't do with normal USB, like plug in an external graphics card or daisy chain up to 6 devices.
The one cable to rule them all.
That's the idea. With Thunderbolt 4 and 5, you can have a dock on your desk with 2 4K monitors, a hard drive, internet, everything, and you connect your laptop with a single thin cable. It charges the laptop and runs all those devices.
That is the dream. No more spaghetti.
For
Okay, we've plugged in the peripherals, we've connected the monitor. I want to grab a screwdriver and open up the case. We're going inside.
the internal anatomy, this is where things get a little more industrial.
When I look inside a PC, the first thing I notice are those flat red cables for the hard drives.
Those are SATA cables. Serial add attachment.
They have that L shape.
Right, that L shape is called keying. It saves a lot of bent pins because you can't plug it in backward. But there's a distinction people miss. That narrow 7-pin cable is just for data. It doesn't power the drive.
Right, you need a separate, wider power cable coming from the power supply unit.
Yes, a 15-pin connector. So every hard drive needs 2 cables, one talking to the motherboard, one drinking juice from the PSU.
Unless you're dealing with really old fans or drives, and then you run into the Molex connector.
The Molex 4-pin, the legacy connector. White plastic, incredibly hard to unplug.
Without scraping your knuckles, I hate them. But there is some useful trivia in those colored wires, right?
There is. If you look at a Molex connector, or really any internal PC wiring, you'll see red and yellow wires. This is standardized. The red wire carries 5 volts.
Okay.
The yellow wire carries 12 volts.
And why does that matter to me?
Well, if you're modding something or troubleshooting, knowing which wire carries the high voltage, the 12V yellow versus the logic voltage, the 5V red, is crucial safety knowledge. You don't want to send 12 volts into a 5-volt chip.
That's a pro tip.
Okay.
Okay, so all these cables, SATA, Molex, they all lead to the mothership, the motherboard.
The backbone. The ATX motherboard is the standard. Think of it like a city map. You have the CPU socket, which is downtown, the traces, the copper wires in the board, those are the highways.
And the parking lots.
In a way, you have DIMM slots for your RAM, your short-term storage, and you have PCIe slots for your expansion cards.
And then you have that terrifying cluster of pins in the corner called the front panel headers.
The headers. This is where you plug in the tiny individual wires for the power button, the reset switch, the little LED that blinks when the hard drive is thinking.
I I feel like I always need a magnifying glass and tweezers for that part.
Everyone does. It's the most delicate part of the build. And polarity matters here. If you put the power LED on backward, the light just stays off. But the power switch doesn't care.
Why not?
Because a switch is just bridging two pins to complete a circuit. It's not consuming power, it's just sending a signal.
It really highlights how physical this digital world is. You have to literally complete the circuit.
That's the beauty of it.
So let's zoom out. We've traced the entire path, from the wall power through the PSU into those yellow and red wires, data across the motherboard, out to the GPU via DisplayPort, maybe daisy-chained, and finally lighting up a pixel on an OLED screen.
It's a complex journey, but understanding the steps empowers you.
That's the so what, isn't it? Why does someone need to know this?
Because it's the difference between a setup that works and one that frustrates you. If your monitor is flickering, you might know to check if you're using an old HDMI cable that can't handle the bandwidth.
Or if your external drive is slow, you check if you plugged it into the wrong USB port.
Exactly. It stops being magic and starts being mechanics. And you can fix mechanics. You stop being a passive user and start being an active administrator of your own tech.
Okay, before we go, I want to throw a thought out there. We talked about Thunderbolt and USB 4 carrying data, video, and massive power, 240 watts, all in one cable.
We did.
And we talked about how PCIe slots on the motherboard are just fast data lanes.
Correct.
Are we moving toward a future where the desktop PC doesn't have internal expansion anymore?
Yeah.
Where the computer's just a sealed brick, and if you want a better graphics card,
Yeah.
you just plug it into a Thunderbolt port externally.
That is the direction the wind is blowing. We are seeing it with mini PCs and laptops already. The internal bus, the PCIe slots, is effectively being extended outside the case via these high-speed cables.
So building a PC might just become stacking external boxes connected by USB-C.
Rather than opening a case and screwing things in, yes.
The death of the screwdriver. Maybe not the death, but certainly a retirement party. The modularity is moving from the inside to the outside.
That is something to chew on next time you're untangling that drawer of cables.
Yeah.
Thanks for listening to this deep dive into the hardware that makes it all happen.
Stay curious.
See you next time.